Hello everyone, my name is Dongwook Go again. Welcome to the second part of the tutorial. And the second part, we will talk about electrical response of angular momentum. And namely, we're going to introduce two different effects which are very important in orbitronics. The first one is orbital Einstein effect. That means electrical generation of orbital angular momentum density. And the second effect that I want to introduce is orbital Hall effect. That is electrical generation of Hall currents that are polarized with angular momentum. So the main question that we like to ask in this part of the tutorial is what happens when we apply an electric field on orbital textures. So in this case, we can expect two different effects in bigger sense. The first type of effect that we would expect is the change of occupation functions, which means by momentum relaxation, we can shift the occupation function. And this can result in very non-trivial effect if there is orbital texture, angular momentum texture in equilibrium. As you can see here, if we have the Rajba texture, if we change the occupation function to minus ky direction, we see that we populate more electrons with minus Ly state, and then we depopulate states with plus Ly states. So therefore, at the end, we expect that there will be more minus Ly accumulation. And yeah, the manifestation of this equilibrium orbital angular momentum occurs if there is already texture in the ground state. And this is called Einstein effect, orbital Einstein effect. And the second type of effect that we expect from electric field is more subtle and it's actually more fundamental, in fact. And this is about change of quantum states. So this has quite non-trivial manifestations, even in systems where angular momentum is entirely quenched. For example, in this case, with tangential orbital texture that we learned in the first part. So what happens with the electric field is that we kick the momentum, and when we change the momentum, then now the electronic states are no longer stationary because crystal potential or orbital texture interactions are momentum dependent. So therefore, the quantum states will evolve over time. So depending on the momentum, then the dynamics of orbital characters will lead to orbital angular momentum. And this coherent hybridization and dynamics of orbital textures can lead to momentum-dependent generation of angular momentum, and momentum-dependent angular momentum leads to orbital Hall effect. So let's take a look at these two effects more in detail. But to proceed, I have one slide on the role of spin-orbit coupling as a comment. Spin-orbit coupling in general in solid state is written in the following form. S times gradient of potential V times P. But gradient of V is, in fact, mostly strong near atomic cores. So therefore, you can have a spherical approximation near atomic cores because that's where the potential gradient is the strongest. So at the end, you can turn this into a very simple form that is proportional to S dot L. And this is the spin-orbit coupling around atoms. I want to emphasize that although there are many different names of spin-orbit coupling in literatures, sometimes like Rajba spin-orbit coupling, Terzalov spin-orbit couplings, they are in fact all derived from the atomic spin-orbit coupling. And different spin-orbit couplings are not different, doesn't mean different interactions. So as an example, let's take a look at the case where we have orbital splittings with orbital angular momentum texture by Rajba effect. So we first have inner splittings of orbital levels depending on orbital chirality in the momentum space, as we learned in the previous part. And then the role of spin-orbit coupling is that depending on the relative orientation of the spin and the orbital angular momentum, you have additional spin splittings within the orbital splittings as shown here. So this clearly demonstrates that spin splittings are derived from the orbital splitting together with the spin-orbit coupling. So therefore, spin splittings of different kinds, in fact, are not independent from atomic spin-orbit coupling. And you can apply a similar hierarchy for non-equilibrium states as well. So assume that we have non-equilibrium angular momentum and non-equilibrium orbital currents. And if there is spin-orbit coupling, and this can become non-equilibrium spin and thus spin currents. And this process is called orbital to spin conversion in many literatures. And the main point of this slide is that many orbital effects are quite fundamental to spin effects. So that's why many orbitronic effects are very important, not by themselves, but also for spintronics and spin transport phenomena. So now let's start with Ed-Einstein effect. Ed-Einstein effect is first introduced by the following paper by Ed-Einstein in 1990. And the phenomenological definition of Ed-Einstein effect is that induced spin or orbital magnetization by electric current or electric field, as is schematically shown in this figure, that I have taken from a very nice review written by Annika Johansson in 2024. But in fact, what really brought life into Ed-Einstein effect was the following theoretical proposal by Manxiong and Zhang in 2008. And they have made a prediction that Ed-Einstein effect can be used for electrical manipulation of magnetization. And this inspired numerous experiments in the past decades, including one of the first kinds by Miron and Gambardella in 2011. And this effect is nowadays called spin-orbit torque. And I'm gonna cover this topic in the third part of the tutorial. But for a long time, in fact, orbital part of the Ed-Einstein effect has been rather overlooked. I don't know the reason, but anyway, the orbital Ed-Einstein effect was first proposed, or rather rediscovered in this paper by 2015 by Yoda et al. By looking at these helical structures. And the reciprocity of Ed-Einstein effect was also shown in this paper, Zhong et al. 2016. And nowadays, we learned that there are many other systems where orbital Ed-Einstein effect is so important and very large. But before we discuss that, let's look at how we mathematically describe the effect. The simplest type of way to describe Ed-Einstein effect is by looking at semi-classical Boltzmann equation. And the semi-classical Boltzmann equation can be derived starting from Liouville equation. And Liouville equation in Hamiltonian dynamics means that the phase space volume or density is constant over time, as that is, the phase space density rho is stationary. So we have this differential of rho equals 0. And then you can actually reduce this equation in terms of single particle distribution instead of n particle distribution function. And this process is called the BBGKY hierarchy. And by assuming that distribution of different particles are uncorrelated by molecular chaos, we get the following equation. And the left-hand side of the equation is identical to the flow part of the Liouville equation. But instead, we can use the group velocity of band electron and occupation function of the band electron. And that's why actually we call it semi-classical. It's classical equation, but we use information from the quantum mechanical calculation of the band structure. By the way, on the right-hand side, which is extra term at the cost of describing as a single particle, this is called a collision integral. And this is because the single particle system is no longer a closed system. It means that it interacts with the rest of the particles and also the environment. And this is the cost that we have to pay mathematically. And there are many ways of approximating collision integrals. But one of the simplest kinds is actually called relaxation time approximation. And this can be written as a simple decay rate equation, as you know. So that is the change of the occupation will depend on the how much occupation function deviates from the equilibrium 1, and the rate is inversely proportional to relaxation time tau. And in this approximation, by plugging into the equation above, you can solve the equation in the stationary state. assuming that nothing changes in time in DC, so the first term chain is vanishing, and assuming that the occupation doesn't depend on space, meaning that we are looking at spatially homogeneous system. And the occupation function can be easily obtained in the way that it's nothing but the change of occupation function in the momentum space, as is schematically shown here. So the change of momentum delta K is proportional to E electric field times momentum relaxation time divided by half R. And this can be turned into a simple form by differentiation by parts. So basically, we get velocity together with the energy differentiation of the occupation function. So with this, we can get then finally the induced angular momentum, orbital angular momentum by electric field, and the susceptibility or response function can be written as the correlation function between the orbital angular momentum expectation value and the velocity expectation value for each band multiplied by the Fermi-Dirac distribution function at the Fermi surface, energy derivative of it. So we can apply this expression to many other models or real material systems as long as we have the information of the group velocity and the orbital expectation value of each band. That's what we are going to do. So let's consider a simple model with orbital Rajba interaction. So this Hamiltonian has several terms, kinetic energy, and the second part is orbital texture term, leading to splitting between radial and tangential bands, and then we have planar anisotropy term. And the physical meaning of this 1 minus LZ square is the projection to PZ manifold. So it means the PZ orbital bands have more on-site energy and more kinetic energy by delta and beta respectively. It's quite intuitive because in 2D system, PZ orbital will be different from PX, PY orbital. And finally, we orbital Rajba interaction due to broken mirror symmetry with respect to the XY plane. And I leave solving this Hamiltonian to you, and you can solve and obtain the band structure and also the orbital angular momentum expectation value. There are two regimes that you can study, whether there is avoided crossing, where there is no avoided crossing, and whether there is avoided crossing. And this depends on the parameter regime. For example, when this condition is satisfied, then PZ orbital band and P radial band will not cross each other, and then their angular momentum will have the opposite signs. As you can see here, slightly positive for LZ, that's also a PZ band, and then slightly negative for P radial derived band. And the Ede-Einstein tensor as a function of Fermi energy shows the following trend. So it first increases, and then it starts to decrease. And this trend is coming from first the positive contribution from P radial band, and then once the Fermi energy reaches the band bottom of PZ band, it starts to decrease because angular momentum is the sign is opposite to the sign of the PR band. But when there's avoided crossing, actually, it's more interesting because as you can already see here, angular momentum can be extremely high, reaching almost one full quantization value. So PZ band goes like this, and P radial goes a bit like this. And this also shows very interesting, very non-monotonous evolution of the Ede-Einstein effect as a function of Fermi energy. And so first, avoided crossings can substantially enhance the orbital Ede-Einstein effect from this simple analysis. And the second, you see that when there is avoided crossing, you have highly non-monotonic dependence of the Ede-Einstein effect as a function of occupation. So these kind of features can be, for example, to electrically detect the orbital texture in experiments. And what about real materials? There are many examples of interface and surface. For example, orbital Ede-Einstein effect can be really strong in STO surface and interfaces, as was analyzed in this paper by Annika Johansson and Ingrid Matic et al. And they have shown that, in fact, really most part of the Ede-Einstein effect in this system is orbitally driven. So spin part, which is red, is so small compared to the orbital part, which is blue. And another well-known example in the field is a copper film, which is oxidized on the surface. And as we have discussed already, it has very strong orbital angular momentum texture near the Fermi surface. And this actually results in very strong orbital Edelshtein effect, induced angular momentum by electric field near at the interface between oxygen atom and copper atom. And the magnitude for the spin effect is actually way smaller, about 20 times smaller than the orbital signal. The whole signal for the spin is actually 10 times magnified. Otherwise, it's too small. So this so far was a discussion on Rashba effect, Edelshtein effect, sorry. So now let's turn our gear to orbital Hall effect. Now, orbital Hall effect was actually proposed already in 2005 and 2009. And in the first paper, 2005, by Bernavik et al., they analyzed the whole band, valence band of silicon, analyzed the following Hamiltonian. And you immediately notice that this is nothing but the orbital texture Hamiltonian that we discussed in the first part. And the second work by Contani et al. Was actually far more surprising, that orbital Hall effect was extremely large compared to the spin Hall effect. And they propose a theory that the origin of spin Hall effect is in fact orbital Hall effect. It was more surprising to me because in most transition metals, we have thought long time that orbital angular momentum is strongly quenched. And the band structure will be very different from semiconductor systems where we still have relative spherical symmetry near the valence band top. So let's try to look into details of orbital Hall effect. To understand what happens when you apply electric field in orbit on top of orbital textures, let's try to analyze simple two-level dynamics. So here I have taken the orbital texture model that we have analyzed before with the tangential band and with the radial band. And now what we are going to do is we apply electric field in a way that we shift one of the states to another momentum value. And this state is no longer actually stationary, as I said before. Actually, the eigenstate at this momentum value is this one with transparent orbital and all the other one. They have different energies. So therefore, the starting point, which was the tangential state at the original K point, if it's written in terms of the tangential and radial state, in the shifted momentum value, K plus delta K, and then they will evolve with different rates. And then the relative ratio between alpha and beta will depend on how much actually we kick the momentum. So eventually, what you see from these dynamics is that because the rate of the oscillation is different, so you have a coupled oscillation between LZ and the orbital quadruple moment. That is the product between Lx and Ly. So we have, first, you have no orbital angular momentum in the beginning, but orbital angular momentum can arise with the drop of quadruple moment, and they have coupled oscillation between the two. And the coupled oscillation between orbital quadruple moment and dipole moment seems like quite general feature of orbital dynamics, as was pointed out in this paper by Han et al. 2022. But very important message here is that even for orbitally quenched systems, orbital angular momentum can appear in non-equilibrium through quantum mechanical coherent dynamics of orbital textures. And this is in fact what is happening in DC electric field. And in DC, radial and tangential states can hybridize and form a stationary quantum state in the following way. And this description can be done by Kubo formulation, for example, or first order perturbation theory by electric perturbation. And this means that we have a hybridization between radial and tangential band with the coefficient minus I in front. This is very important because this means that this stationary state will have finite angular momentum. And the result is that in the stationary state under DC electric field, L is induced in the direction of E cross K for the simple orbital texture model. So this means that for two-dimensional case space, as an example here, LZ induced here for states with positive KY when we apply E field along X direction, and the induced LZ will have the opposite sign for the states with negative KY. And because states here with positive KY, they already move with the velocity of positive group velocity, while states here, they move to the negative Y direction. And this explains the emergence of orbital Hall effect in the stationary state. And orbital Hall effect is, in fact, in this case, is the result of the induced angular momentum by electric field, by magnetoelectric coupling. And the intrinsic nature of the effect is due to the fact that the velocity that is carrying orbital angular momentum is the ground state velocity of the individual bands here. And orbital Hall effect exists in many different materials because orbital textures are quite ubiquitous in many multi-orbital systems. And orbital Hall effects in tracer metals have been studied in many different works, already from Kontani and Tanaka, and by Dagon Zhou, and by Salemi and Openier, and also by myself. And this view graph shows the orbital Hall conductivity and spin Hall conductivity of all D transition metals. And the first thing that you notice is that orbital Hall conductivity is way bigger than the spin Hall conductivity when you look at the scale of the plot. And the spin Hall conductivity is large, mostly for some of the outstanding metals for spin-orbit coupling. We know already, tungsten, platinum. That's why people have focused on tungsten, platinum for quite a lot in the past due to their large spin-Hall effect. But when you look at light metals like titanium and chromium, their orbital Hall effects are still gigantic, while their spin Hall effects are almost vanishingly small. And that's why actually early experiments which try to measure orbital Hall effect in metals focused on titanium and chromium, they were confirmed in the following two papers by Che and Lilan et al. On titanium film and chromium film. And also in the past, there was an experimental work that measured spin Hall effect in platinum and tungsten metal films. But in all three experiments, the experimental geometry looks like this. So I've taken the figure from the first experimental paper, 2023. So we apply electric field, electrical current leads to orbital accumulation at the top and bottom surfaces. And then we measure induced angular momentum or induced magnetization on the surface by polarized light. And this effect is called magneto-optical Kerr effect. And this is a quite standard method nowadays to measure surface magnetization. And the experimental result shows that the Kerr angle, there's a rotation of the polarization by light, is linearly proportional to current density you apply. So it means that this is a current-induced effect. But the question is actually how you know that this is coming from the orbital accumulation, not the spin. Here comes very important realization. And that is light interacts with the orbital part, specifically orbital dipole moment of the light, of the wave function. And then we can detect spin by light because of the spin-orbit interaction. So that's why when you look at the expected amount of Kerr rotation for the given amount of orbital accumulation and spin accumulation, in fact, spin accumulation can give rise to about 100 times stronger response than what spin accumulation can give. So orbital is way more susceptible to light than the spin. And this is in fact already was explained in the following book chapter written by Peter Openier in 2001. So magneto-optical response doesn't appear without spin-orbit interaction. Okay, and the orbital Hall effect also occurs in many different systems, not only for central symmetric systems, but systems with broken inverter symmetry. For example, the transition metal dichalcogenide is a good, well-known example with broken inverter symmetry. And the band structure of, for example, MOS2 looks like this. And then we have direct band gap and K prime points, and they are called valleys. Maybe some of you know very well from 2D materials. And the effective Hamiltonian of this material is written as a gapped Dirac model. And Q is the momentum measured from K or K prime, and tau is plus minus 1. That is basically the index for K or K prime valley. Here, a very important point is that the basis functions of this effective Hamiltonian, the basis functions for the conduction band is z square orbital, while the basis function for the valence band is xy plus I times x square minus y square orbital. And this state carries plus minus half r. And this is often unnoticed, but this is extremely important in understanding the Hall effect in the TMD systems. So it means that first, if you calculate the valley curvature in TMD from this gapped Dirac model, you get the valley-dependent valley curvature. And this is one reason why we have the valley Hall effect, right? But at the same time, when you look at the orbital valley curvature in the following form, orbital valley curvature doesn't depend on the valley. And the reason is that first, we have valley-dependent orbital angular momentum because of this. The basis function itself carries plus minus 2 half-r in each valley. So valley-dependent orbital angular momentum combined with valley-dependent valley curvature leads to finite net orbital valley curvature. And this is the reason for the orbital Hall effect in TMD systems. So basically in this system, the orbital Hall effect is driven by the valley curvature combined with angular momentum, which are already present for the ground state wave functions. But then there's a question whether valley Hall effect is related to orbital Hall effect or whether they are different. Well, we can ask the following question. What is really the physical observable associated with valley? It's a bit obscure, in fact, because valley is more defined by human. It's not naturally observable quantity like velocity or position or angular momentum. But what makes valley really experimentally accessible is, in fact, valley-dependent orbital polarization, as I pointed out in the previous slide. So in fact, many optical detections of valley Hall effects, if you look carefully, they in fact measure orbital angular momentum of valley electrons. So therefore, there was a paper arguing that we should rather call valley Hall effect valley orbital Hall effect to emphasize its physical meaning. On the other hand, if you start to look at then bilayer systems of TMDs, then because there is inversion symmetry, there's no more valley contrasting valley curvature. Or, okay, for example, there's layer 1 and layer 2. And then layers, they have cancellation of valley curvatures precisely. But nonetheless, you can still have non-zero orbital valley curvature that are hidden in each layer. Therefore, orbital Hall effect can still manifest, even if there's no valley-dependent valley curvature. So it means that, again, orbital Hall effect is quite fundamental. But although I discussed a lot of mechanisms on orbital Edelstein and orbital Hall effect, there are missing contributions that are currently actively studied. The first effect that we need to consider is disorder scattering. This can lead to, for example, skew scattering or side jump. Skew scattering is like billiard with spinning ball. So different spinning balls will have different scatterings. And side jump is more delicate. It's related to the momentum-dependent position that is basically anomalous position. So momentum change can lead to the shift of the anomalous position. And in the following works, they discuss the role of disorder scatterings, and some have shown that disorder scattering is quite crucial for orbital Hall effect. And another important effect is that although so far we focus only on the atomic contribution to angular momentum, there can be intersite or I-turned angular momentum. And And this is also quite actively studied nowadays in many other works. And if you are interested, I recommend you to read the following recent papers by many others. So to summarize the part two, we look at orbital attached time effect, which means current-induced accumulation of angular momentum. And this is due to shift of the occupation function by momentum relaxation. And this results in accumulation of orbital density. And orbital Hall effect is coming from coherent superposition of orbital textures, or in inverted symmetric broken systems, this can arise due to unquenched angular momentum in the barrier curvature. So so far, yeah, that's it for the second part. And yeah, see you next time. Bye.